No doubt, there are some really big questions out there when it comes to life, existence, the universe, everything we can conceive of. And yet, we very rarely ask ourselves, we very rarely decide to tackle the biggest questions of all. And that includes, what is the entire universe? What is it that's out there? Where are we today and how did we get here? And finally, where are things headed in the future? There's a big universe out there, but thanks to science, inquiry, and the power of human ingenuity, we're actually able to investigate those questions and for the first time in all of human history, come up with an actual understanding of what those answers actually might be. Want to find out more? Stick around. We're going to take these questions on this year-end Starts With a Bang podcast. For centuries, the question of what the universe is and where it comes from was a question for the realms of poets, of philosophers, and of theologians. But today, we think we actually have a legitimate answer to the best of our abilities, and that answer comes to us directly through the power of science. The power of scientific investigation is the power of finding things out. What you do is you look at the universe, you look at the world, you look at natural phenomena itself, and you find a way to ask it questions about itself. How do you act under these circumstances? Well, we can do an experiment. How do things in a condition that we can't experiment on actually play out? Well, we'll go and look for a natural instance of where that's actually occurred. For us and our position in the universe, all we have to do is look up. If you look at the night sky and wonder, what is all of this? You have only to look at our scientific history to find out what those answers are. If you look up at the night sky, you'll notice over a single night, those stars rotate around a single fixed point. That's the poles. North Pole if you're in the northern hemisphere, South Pole if you're in the southern hemisphere. If you come back night after night after night, you'll notice that every single point of light in the sky is in the same relative position to one another. Those are the stars. You'll notice a few that move night to night. Those are the planets. We measured planets by watching how they move night to night. And just through those observations, we were able to figure out a whole slew of incredible things, like what the laws of planetary motion are, what the configuration of our solar system is, and beyond. We've been able, just by looking at the stars, to figure out, first with our naked eye and later with telescopes, spectrographs, and more advanced equipment, what it is that they're made of, how far away they are, what makes one type of star different from another. We've been able to learn all of this just by asking the universe about itself. We learned that there are different star types, they come in different colors, they're made of different things. There are even different populations of stars. Some stars are like ours, others are far poorer in heavy elements. They're less enriched. In theory, we can even go back in time and find the very first stars ever formed in the universe. We see, when we look out into the universe, how stars form, where they're born, and how they die, how they go through their life cycles and die, either in planetary nebulae if they're around our sun's mass, or a supernova explosion if they're much more massive. We look at these star-forming nebulae, at these star-forming regions out there. We look at stars with different populations. We look at the remnants of planetary nebulae and supernova, and we can see that there are new generations of stars forming out there on a continuous basis. But that's what we get just by looking in our own cosmic backyard. The universe itself is so much more than just stars and planets. That might be everything that we find of interest, with the addition of gas and dust and some other little bits of matter in our galaxy. But our galaxy is one of perhaps 2 trillion in our visible universe. We can look beyond the Milky Way to the great spirals in the sky beyond, and what we discover is that they themselves are galaxies all unto themselves. We first looked at these objects and didn't know what they were. It wasn't until the mid-1800s that we had telescopes large enough that we could determine they had a structure to them, that they were more than just these diffuse clouds. It was the invention of astrophotography and its application to these spiral nebulae that allowed us to see how intricate this structure is. The first picture of a galaxy beyond our own was taken way back in the 1880s, and if we look at that photo today versus a modern photo of the Andromeda Galaxy, we see that virtually nothing has changed. But what we do find is individual stars in every galaxy we look at. If it's close enough that we can resolve individual stars, we can see what properties they have. And what that enables us to do is determine a distance to them. That's how we found these were galaxies far beyond our own, that these were what we called then island universes all unto themselves. And what we found furthermore looking at them is the farther away they are from us, the faster they appear to be moving away from us. How do you measure speed? Well, remember, light is a wave, and it has a particular wavelength. If something is moving towards you when it emits that light, it's going to have its wavelength compressed, or what we call blue shifted towards higher wavelengths, towards bluer light. On the other hand, if it's moving away from us, it's going to be red shifted. It's going to be shifted towards longer wavelengths. And so what we find is the farther away a galaxy is, the more redshifted its light is. Either this is because everything is speeding away from us, and we're at the central point here, or the fabric of space itself, consistent with Einstein's relativity, is stretching and expanding. And the more space there is between you and a distant galaxy, the more we see the effects of that expansion, and the more that light gets redshifted. This led to an incredible idea. We said, if the universe itself is expanding, if the fabric of space itself is being pulled apart, what does that mean? It means that as time goes forward, things are getting less dense. Light itself is continuing to redshift, so the universe is cooling. And if you look at a universe that's expanding and cooling today, what does that mean if you look back in time? It means at earlier and earlier times, this big expanding cooling universe today was hotter and denser the farther back in the past you go. So this is where the whole idea of the Big Bang came from. We decided, you know what, if you make this extrapolation based on what we see and you go back, what else happens? You think about, okay, if we have an expanding cooling universe today, then it was hotter and denser in the past. What happens if we go to a hotter and denser past? What does that mean? What does that look like? Well, you can say, well, as time goes on, gravity has more time to pull things together, to cause gravitational collapse and to cause clumping. What that means is over longer and longer times, structure gets more complex. We start to see more evolved structure, more complex structure as we come forward. So if we look back to the distant universe, light takes a finite time to reach us. If we look at things many, many light years away, where the light took 1 billion years to travel to us, when we see that distant object now, we're seeing it as it was 1 billion years in the past. So this tells us that we should see less evolved structures in the past. We should also conceive that, you know what? If we go further and further back, there should be a time where gravitational collapse hadn't yet pulled anything into these bound collapse structures. There should be a first star and later on a first galaxy in the universe. If we go back even before that, you can say, well, if all we had was this matter, but we had radiation that was this wavelength, that was a certain energy, and then it was a shorter wavelength or a higher energy, and higher and higher and higher, the further back in time we go, there should come a time where this radiation was so hot that you can't even form neutral atoms. This leads to the idea that there would be a leftover glow from the Big Bang, a cosmic background of radiation that by time we look at it today should have redshifted so far it shouldn't be visible light or even infrared light. It should have redshifted all the way into the microwave portion of the light spectrum. And so you say, okay, can we go back even further? Yes, you can. Maybe it was so hot, that energy was so high that you couldn't even form atomic nuclei. The instant you brought a proton and a neutron together, a photon came along and blasted them apart. So we should get a prediction out of this for how the first elements fused together. That we should get a prediction for how many light elements should have been formed in the very early stages of the universe. And finally, we should be able to go back far enough to a time where you can say, what if we bring everything back arbitrarily to a singular beginning, to a point, to a time where all of time and space and matter and energy were compressed down to a single point. We call this a singularity, and this was the idea for a long time, that the Big Bang would lead to a singular beginning for the universe. But does it? How much of this is true? This is all a grand idea, but it also sounds like a house of cards. This is where the science comes in. It's not just an idea. It's something that you have to be able to go out and test. And then you can apply the lessons you learned from looking at what the universe tells us about itself to our very picture of what existence is and what it's all about. Well, guess what? We've done all of this. We've confirmed so many of these things just by looking out at the universe itself. You measure distant galaxies, and what you can see if you look today at how many galaxies there are in a given volume, and how many galaxies there are in a given volume back in time, and you can see there were more galaxies in a given region of space at earlier times. We can see the universe is getting less dense as time goes on. You can look back at these more distant galaxies and you can say, what about the light coming from them? Do they show evidence that these galaxies have evolved into the ones we see today? Yes, they have. Galaxies in the past were bluer, intrinsically telling us that they were made of younger stars. Galaxies in the past were smaller, telling us that they've merged together over time under the influence of gravity to form the behemoths we see today. And finally, we see as you go farther and farther back in time, farther and farther to greater distances, we see that there are more spirals and fewer ellipticals, because elliptical galaxies require the major merger of large spiral galaxies to make an ellipse. Back in the early stages of the universe, there wasn't enough time that had gone by for all that to happen. You can measure the populations of stars and see today we have more heavy elements. They're more enriched. In fact, if we go all the way back to the very first light and stars we find there are gas clouds along the way that have never yet formed stars. They're made exclusively of hydrogen and helium, these pristine elements left over from the Big Bang. We can even look beyond what Hubble or any of our great observatories have seen to the distant universe before there were any stars or galaxies. And what do we find? We find a uniform background of radiation, just 3 degrees above absolute zero. This is the vaunted cosmic microwave background, the leftover glow of the Big Bang itself. It's here, it's real, and we can access it today. So you look at all of this and you can say, oh wow, maybe there was that singular beginning. But there actually wasn't. We know this by looking at the details of the Big Bang's leftover glow. You look at the details and you can see here is how large the temperature fluctuations are. These fluctuations come about because your young universe is made of matter and radiation. Matter works to gravitationally collapse, but radiation exerts pressure. If you make an overdense region, that radiation pressure is going to push things apart again and try and prevent things from collapsing too quickly. So back before the cosmic microwave background, when everything was super hot, dense, and ionized, things are scattering off each other. Matter tries to collapse and radiation pushes it back out. It's only when you make neutral atoms that the matter falling in for the first time that's about to be pushed out by radiation suddenly doesn't get pushed out anymore. That's the critical scale that we should start forming structure at. And the smallest bound structures we see in the universe, the smallest galaxies, globular clusters, they correspond to that exact mass scale that we see. Furthermore, you can say how big are these fluctuations, and you can determine that there's a maximum temperature the universe reached at the start of the Big Bang, and it tells you you can't go all the way back to a singularity. There has to be something cutting you off from reaching these arbitrarily high temperatures. So everything is confirmed except that last prediction, except the most extreme one. There was no singularity at the start of the hot Big Bang. Instead, if you come to our modern way of thinking, we believe now that there's a phase before the Big Bang known as cosmic inflation that sets it all up. There's so much that we've learned about what this universe is, about where it came from, and where it's headed into the future. We wondered for a long time, will the universe that's expanding turn around and recollapse and end in a big crunch? Will it continue coasting forever and continue to expand, almost recollapsing but not quite? No, neither of those. What we found instead is the universe's expansion. It expands, it expands, it expands, gravity fights it, it doesn't win, and then all of a sudden it speeds up. Things start moving apart from each other faster and faster and faster. This was the discovery of dark energy made in the 1990s through distant observations of the universe. As time goes on, all of the unbound structures, galaxy clusters, groups, and filaments are going to separate. When we look to our far future, it's going to be just our local group, the Milky Way, Andromeda, and maybe 60 small galaxies, and that's it. Everything else beyond our local group, even the massive Virgo cluster or supercluster, even the huge thing we're part of, the largest structure we know of, Laniakea, is not bound to us. Over time, this will all redshift away. We know about dark matter, the unseen mass that holds the universe together, and we know this because of the observations we've made of the large-scale structure of the universe itself. We've learned these things because we ask the universe questions about what it itself is doing. This is the most you could possibly ask for. Ask the universe, what are you all about? It tells you the answer. That's how you figure it out. Don't ever listen to anyone who tells you the path to knowledge is by trusting an authority. The only authorities worth trusting are the ones who can tell you how you can learn this for yourself. How you can figure it out if you didn't know the answer by doing the investigation, the observations, the experiments, the calculations, all of it for yourself. You can, and that's the unique beauty of science, is that anyone can do it, anyone can learn this, and the fruits of our labor, the full suite of knowledge that we've accumulated, as well as the process of refining and further testing, is something that's available to us all. The journey has not yet ended. Even though we know about cosmic inflation, dark matter, dark energy, we still have so much more to learn. There's a cosmic story out there that unites us all, and we're lucky enough to be here at the end of 2017 seeing what this story is, how it comes together, and if we want to know about it, all we need to do is ask. It's up to us to value this cosmic story, to share in its glory, and to share that glory with others. It's a great unifier and the story of every living creature here on Earth. We all share the same cosmic origins. If you want to know the answers to the biggest questions of all, know that science won't ever reveal the final answer. But whatever answers we do come up with will have to be consistent with that full suite of knowledge that we've accumulated. If we want to be honest with ourselves about what all of this is, where it all comes from, and where it's all headed, we have to listen to the ultimate source of truth, what the universe tells us when we ask it about itself. Thanks for listening to the Starts With a Bang podcast. It couldn't happen without the magic and the help of our valuable Patreon supporters. I'd like to thank everyone donating to us at the $5 a month level and above. Thanks to Rob Hansen, Bakhtiar, Chris Shaw, Thomas Sola, Denier, Pedro Texera, Igor Mitrofanov, Sean Foley, Elver Sena Sosa, Flo, Richard Jousey, DGE, John Kozura, Marcelo Barnaba, Nick Tomlinson, Rafal Wojciech, Danny, Alexander Marius, Guy Jin, Andrew T. Douglas, Chris Hilly, Weller Tractor Salvage, Rana Nyechezel, Ron Lyle, Frank, Paweł Zuzelski, Fraser Kane, Steve Shaber, Naked Bunny with a Whip, Jason Basanseni, Frederick Y. Martello, Peter Williams, Bill Murphy, Mark Armstrong, Kevin Barnes, Patrick Dennis, Radek Nesbida, James Nance, Joe McFarland, Amira Sosnick, Rachel Merritt, Sydney Atwood, Jose Enrique, Harry Plumley, John Methot, Nathan Hanna, Thomas All, Glenn McDavid, Benjamin Turner, David Taschioni, Joe Latone, Philip Radulovic, John Seal, Braxton Thomason, Karen Garrison, and Zarko Opachik. Thanks for tuning in, everybody, and we'll see you next time here on the Starts With a Bang podcast.